that or not. So the topic I will be going to be talking about are spanning time and spatial scales, and we'll be talking about the modeling of our planet's climate, and I'll be focusing primarily on the physical climate. I work in this place in Princeton. I've been there for a long time, and we start in our work with the global perspective. So this picture up there is from one of our global climate models showing sea surface temperatures. Pretty image, but it's where our state of knowledge is and how we can take what we know and convert it into computer models. We start there, global scale. You all may be often interested very much in the local scale. So how do we bridge that gap between large-scale physical climate science, more local scale and regional scale, not physical climate, ecosystems, water management, cultural, pick your favorite impact. That'll be what I'll try to give you an idea about. So we were asked, speakers, to talk a little bit about yourself. You folks all had one slide. Also feel free to ignore the slides. They're more to remember, for me to remember what to say next than for you to have to look at. But hey, I'm old enough that when I was a little kid in grammar school, 1969, my parents let me stay up to watch the men land on the moon, July 20th, 1969. And it was even neater for me because the second man on the moon, Buzz Aldrin, he was from 2 towns over in New Jersey, right? So it was like, ooh, this is cool. That's what we called reality TV. That's how long ago it was. But I got interested in science at that time, and it was a couple years later where I learned about Kepler's laws of planetary motion. You know, that whole thing about planets go around an ellipse and the arc, the area of the arc that they sweep out per unit time is the same. I was like, wow. You can actually connect like math with these things that you see through telescopes. That was kind of neat. But that was 1969. Then the next year, what happened, it was the world's first Earth Day. That's the ecology flag, for those who don't know. And that got me to the point where, even at that young age, where I realized I didn't have to just look out to space, I could then look back at the Earth with science. And there were all these other unexplained questions. The one that me growing up in New Jersey was most interested in were snowstorms, because that's when you got days off of school, right? You really wanted to understand that better. So that was the motivation for the little budding weather weenie. Okay, honestly, how many here consider themselves weather weenies? Or reformed weather weenies? Okay, so there's some, not all that many. How many of you have never heard that phrase before? Really? How many of you have ever walked through? Wait, you went on a tour yesterday, right? Okay, you saw weather weenies. Just so you know. So I took that and I went for a bachelor's and got a master's at Rutgers, the State University of New Jersey, and I was lucky. I did well enough in grades that I got asked to do a senior's honors project, right? My first getting my feet wet doing research. Now I look back, and even only a couple years after I did it, it was like, oh man, I could have done that so much better. But I got introduced to the topic, and I thought, well, research is kind of neat. But maybe some of you knew exactly what you wanted to do. So, you know, it's always in between. Been hearing a lot about flexibility. John Zach talked about how the job you have 10 years from now is going to be different than the one I have today. I was also lucky enough to try out a few different things. One thing I had to do between my undergrad and graduate years is I got to work as a part-time radio broadcast meteorologist. I was on 13 radio stations throughout the Northeast. That's kind of like a part-time substitute for a guy who was changing from one company and was out on his own. And so that was like baptism by fire, right? You're sitting there in one office on a phone. I had his roster of 13 radio stations calling up, doing live bits, 30-second, 90-second, 60-second. And there were some really tough parts. Some days were boring, I found. Some days, with 13 stations, the day when that cold front's moving through in the summer and there's tornadoes going through Massachusetts and it knocks out your power so you can't get the radar, but the phones still work. Stressful day. But the toughest part was the biggest radio station we had at that time was WITS, your 50,000 watt clear channel home for Boston Red Sox baseball. You don't know how hard for me that was to do. Having to get up at like 5 o'clock or 4 o'clock in the morning to go and do that and then say that. You see, I grew up 9 miles from Yankee Stadium. Anyway, that was tough. So I learned there were things about that I liked, things I didn't. I also had opportunities to do a little bit of work with the state agricultural meteorologists. Yes, New Jersey has agricultural meteorologists because there's a decent amount of agriculture, especially in the southern part of the state. And that got me a little bit of, I was just doing kind of hourly work, doing some research and that, but I also needed to communicate to the farmers. I had to learn about what haying conditions were and what made for good haying conditions, and then communicate that information to folks. So bridging the gap between the weather-weenie nerd science who wanted to talk about relative vorticity and haying. I also got to do some work with the chairman of our department who had like a consulting business on the side, and I got to do some consulting work, preparing legal testimony, doing some statistical research. That was kind of neat. And those of you from Oklahoma, University of Oklahoma, we join you in mourning the passing of Peter Lamb. I'll let you know that that first consulting work I did, it had to do with something that was going on in the gas service company of Kansas City, Missouri, and the way that natural gas rates were set. And on the other side were Stanley Changnan and Peter Lamb. And on our side, there was Mark D. Schulman and this goofy little student, me. Anyway, so that was my introduction to Peter Lamb. And oh, by the way, we won. So, okay, won from him. So I learned that. But from what I learned from all that is that when I got the opportunity, when I was finishing up at Rutgers, I had an opportunity to go fresh from there to GFDL, this place where the world's first coupled atmosphere ocean climate model was produced. The paper, no, it wasn't. The paper was 1969. This was the 1980s when I went there. And my first boss was this guy, Kirk Bryan. My second boss was that guy, Suki Minabe. They're giant in the field. The people whose names were all throughout the textbooks, I got to go work for. So I took that job, and as it turns out, I've been there ever since. So it sounds like, oh, you had one job and that was it, but it keeps changing, right? We've gone from black and white images like that to now, this is what, when I'm doing my research, these are the kind of images I make to do my research, but they're also kind of pretty, right? They ended up on a postage stamp. That's pretty awesome, too. But anyway, true, I'm not making it up. So I've been there for more than 25 years now. The job, my job title is actually the same, the way the government works. But a lot has changed with the job. You've heard about that before. Keep that in mind. Also, the public perception has changed. When I first started out there, if I was at a neighborhood picnic, barbecue, people ask, what do you do? Well, I do computer modeling of the world's oceans and atmospheres to study climate variations. What do you do? I do that. What do you do? You went to college? Yeah, I went to meteorology. Oh, are we going to see you on TV? That was what it was like. It wasn't on people's radar screen. Fast forward, then, after I've been there for maybe 10 years or so, people had started hearing about climate. It was a period of curiosity. I went to another barbecue and talked about it. Then it was like, oh, I've heard about that. Could you tell me more about this? Now I'm at a stage where those barbecues aren't fun anymore. Because when I show up and I say that same exact thing, 2/3 of the people decide they know everything about me. They equate a physical climate scientist with a climate advocate, right? They can't tell the difference between somebody who took 4 semesters of calculus as an undergrad to do meteorology versus somebody who works for Greenpeace writing press releases. So half of them hate me because I'm the evil on that side, and half of them want to adopt me and get angry when I don't necessarily agree that the only way we're going to save the world is by all wearing hemp clothing or something. I mean, it just doesn't, they stereotype me, and it's just kind of tough. So anyway, things will change, not just in what you do. And so, okay, bottom line from this introduction, there's a limit to career predictability, right? We can talk about limits to predictability of weather and climate. There's also a limit to your career predictability. Be flexible. So there's that little intro. So some things I'll talk about in this freeform thing I'm doing to remind me. Dynamical climate models, one tool in our toolbox of trying to advance climate science. Then I'll talk a little bit about downscaling climate model projections. Some of you may never use the output of a climate model directly. You might go through, only use things after it's gone through a value added, hopefully, step. And we'll also talk about issues about what questions can climate models address, or some of the different factors you want to think about that. And then I also want to pose a question to you about what you think would make a climate model better. So we start off the overused 3-legged sturdy stool. I'm going to be talking about climate models. That's what I was asked to talk about. That's what I was doing. See? Good match. But progress in climate science, why we can say more about things than we could 15, 20 years ago. Why academies of science, IPCC, and other learned bodies can say, yes, it's unequivocal that the planet is warming. Yes, we can say with a high degree of certainty that most of the warming of the last half century can be attributed to human activity. And why? We can also say, you know what, there's more in store, good chance at a faster rate than what we've seen in the last century. Those three things get people's attention. How can we say that? It's not just for models. It's when observations, models, and theory, the understanding of the way things work, when they come together and tell a consistent story, that's when you can get the scientific confidence level up high enough to make those statements. And there's some that aren't there yet. You heard some of the things earlier today where there's still some things that are in the ferment and froth stage. Some of that connection between anthropogenic climate change and what it really would mean for Atlantic hurricanes and that. Some things a little more solid, others in the ferment and froth. So when it all comes together, then we make that statement. However, we also want to note that where the confidence tends to come first is when we talk about large-scale things over multi-decadal timescales. Why that first? You're averaging out noise in effect, right? There's natural variations. There's things going on. There's noisy, twitchy systems. It's not a smooth thing. So the larger the area you average out some of that noise. Start looking at multi-decadal periods and a longer time for the signal of a change to emerge from the background of natural occurring variations. So that's where the science first tends to come with its confidence. It's a solid starting point, but it also is compelling evidence coming together from the observations, theories, and models, telling us about what's changing on the large scale over multi-decadal timescales. When that gets received and gets put on people's radar screens, what do most people then start asking? This happened in the mid-2000s. Less than 10 years ago. It was like almost like a tipping point or a change point there. People then start to ask, okay, you got my attention. Now what does it mean for the thing I care about in my backyard? If you care about a lesser prairie chicken, you want to know about that. If you want to know about how mosquitoes that carry malaria might move around, then you care about that. Water resources, your little catchment basin. How that? You're a Napa Valley wine grower? How's climate change going to affect me? You have a New Hampshire ski resort. What about that? Local scale things. So what people don't realize is that when they ask that question, they've now changed the scientific question so much. They're going to smaller spatial scales and shorter time scales often in their climate impacts. And in many cases, they're interested in going not in how the physical climate is going to change. They really don't care about temperature, precipitation, those sort of things. They care about what it's going to affect. Ecosystems, water resources, things that are integrators, things that also have other things affecting their variations. So it gets to be a more complicated issue. Also, changing tactics just a little bit. The question, everybody kind of clear on when we use this phrase, the differences between mitigation and adaptation? Mitigation, you're thinking about a human intervention that would either reduce the sources of the greenhouse gases or enhance their sinks, right? So sometimes there's focus on that. Then there can be the issue of adaptation. Climate is changing, more is coming. What kind of human intervention can there be to try to reduce the vulnerability of systems, whether they're natural systems, human systems, or managed systems? There have been times, to go back to the mid-2000s again, when a lot of folks viewed these as at cross purposes. People who are interested in mitigation, trying to get cap and trade deals through, and are looking to the scientists and asking us questions. How much confidence do you have in this? What can we say on that? They didn't necessarily want it because they thought that talking about adaptation would reduce the attention on mitigation. However, as a physical climate scientist, I'm agnostic about that. I really don't care. I'm going to just try to do the best science we can do. Try to communicate it to my peers. The stuff that's societally relevant, I will then try to communicate more broadly. And to try to allow people to make better informed decisions. We've heard it before. We're not there to tell them what the decision should be. It's policy relevant, not policy prescriptive. You heard that earlier today. So that's the way we kind of frame it. But it affects the science because I'd say probably about 20% of the questions that I've heard from you all this week weren't about the physical climate science, wasn't necessarily about the direct climate impacts, but was more in this sphere of the policies and how it relates to that, right? So they're always interconnected, but I'm staying upstream a little bit. But we can't be immune from it. You've heard about exercises about going after funding opportunities. Well, where does that funding come from in most cases? Right? A place that has that building in it. And it has an impact on how the science gets used and how it's perceived. In early 2009, I had a conversation with someone who had been the chief of staff for the House Science and Technology Committee. And what he told me was that in his impression, climate science by the year 2007, when the IPCC report came out and the National Academy reports before that, climate science had essentially answered all the questions that needed to be answered for policymakers. Those three things. Climate change, unequivocal, most of it due to human activity, more in the future. The ball was then in the policymakers' court. They may do nothing with it, they may do something, but essentially what he was saying that you've gotten to the levels of uncertainty, you've communicated it well enough as a community, that's what's left now is for the sausage making to happen, or not. That the extra information that was going to come out over time, yeah, well, interesting, wasn't going to really change that. The ball was in their court regardless. So as somebody who does the large-scale climate science, that wasn't necessarily the best long-term answer to hear. Oh, thank you very much. He said it was the best example he could think of in science, where scientists have actually come back in a reasonable time frame, even though it was a couple decades, of a clear answer that was then going to move things across. But his interest was in mitigation. Kyoto, follow-ons, carbon tax versus cap and trade, those sorts of policy issues. So there they had the information. As it happened, just that summer before, when I was at Bill Hook, the Sunday Speaker's Science Policy Colloquia, I spoke with another staffer, who was a staffer at that time for the House of Representatives, someone in the Pacific Northwest. And what she said is, I don't think you scientists realize what you've done by having those same three statements. Because now you've gotten everybody's attention, and you're going to be asked questions that I don't think the science is up for. You're going to be asked for what it means for people in their backyards about the things they care about. What does it mean for the prairie chicken? What does it mean for, pick your favorite aquifer? What does it mean for loblolly pond? What does it mean, all those impacts? Because that's what people care about at the congressional district level, is stuff that's going on there. Can you have that information? Can you provide that? So in a way, you could think of the South Central Climate Science Center and other entities that have popped up since then are trying to help bridge that gap, to try to go from the upstream part of the science down there. So here's how I would describe it. Going from the large-scale science to stakeholders, we start with the parts of the sturdy three-legged stool. We want to have a firm foundation, but that's not enough. There needs to be often a step, what we can call translating and scaling those global climate model simulations. That can involve words, guidance, but it can also involve things such as transforming and post-processing that information. Downscaling is one of the common ways of doing it, but not the only one. But there ends up being an intermediate step, and then that output ends up becoming the input to what I'll call climate impacts analyses, whether you're interested in corn yields in northwestern Iowa or Pinot Noir in Oregon, or anything in between. When the Navy comes and starts asking questions, as they're thinking about when they're going to have to maybe build some ships to start patrolling the Arctic, which they don't necessarily do so much right now. There's all these impacts, but this, as good as it is, doesn't always get to the level that they want, so some additional processing needs to be done. And then that information, then we can have a whole group of people, including social scientists and others, helping us to get this information into a form that's communicated well in order to allow better informed decisions to be made, or not. And then the loop kind of curves. It comes back because there's feedback from those decision makers in one form or another, sometimes direct, sometimes indirect. We just look at the federal budget each year and we figure out the indirect effects of that. So that's a lot of preamble. Here's, we're going to get into a little bit of the modeling of the global climate system. A simple cartoon to me, complex to some, right? Pretty busy. But it's just starting to show some of the different things we need to account for if we're going to study the global climate system in a numerical model. It's not just about the surface climate. You may be interested in the surface climate. We have to spend a lot of time also thinking about the ocean, the deep ocean, not the ocean around here, the ocean in the Southern Ocean. With all these different things. So there's folks who specialize in each and every one of these individual parts that take that knowledge, right, the theory part, the understanding, convert it into computer code to create the models, informed by observations, test it out, put it together, get those feedbacks, test it out, positive, negative, see if it makes sense, see if it works, and then we end up with this big complicated system. So it takes a lot of folks from a lot of different backgrounds. Some people come into it thinking it must just be a bunch of meteorologists and climatologists. These are the different categories of folks and the degrees they have that I can think of that I've probably worked with in the past 5 years, and I'm probably missing some. It's big, complex, interconnected. You end up with different teams working on different parts, and then a great project management issue of getting them all to come together. This is the sort of work that's done at the really high level at a little bit more. It used to be a half dozen, maybe a little bit more. On order 10 modeling centers around the world to do at this level. Because you need to have both the brainware capacity to do it and a lot of computer hardware capacity, because these are big, expensive models. So it's not something that can be just a mom and pop operation to do at the cutting edge part. And it also isn't just about computers. It takes people to come together and do it. So, back to the pretty picture. Why do we go through all this? Well, if I'm giving a talk in an 8th grade earth science class or to congressional staffers, and that thing's on, and you're guessing, yeah, you know, yeah. When we get our little media training and stuff, that's the example. They say you can treat those as equivalent. I didn't say that. I'm quoting someone. How can you perform experiments on the climate system, right? You talk to an 8th grader about earth science, what's their vision of a scientist? Somebody in a lab coat, at a bench, in beakers. How do you perform experiments on your planet? Well, I have to start by telling them, we can't. Why do I do a computer? It's just a model. Well, we can't exactly shrink down the planet, put it into a test tube and do an experiment. We don't have a twin planet Earth where we could double the amount of carbon dioxide, throw it in a time machine. You know, maybe you can write a good NSF grant and build one of those things, and we would appreciate it, and figure out what will happen. So how do we do it? We use a model. We write a model. Our laboratory are supercomputers, and the tools we use, our lab equipment, is the computer code, where we take what's known, starting with F equals MA, and working from there to describe how the planet's climate system and the different components work. So our climate models you can think of as our virtual Earths. They're going to provide a physics-based method to estimate how the planet's climate will respond to a whole bunch of different things. So for this audience, I'll talk about greenhouse gases and other radiative forcing agents. Who's not familiar with the phrase radiative forcing agent? Okay. You can think of a radiative forcing agent is something that will cause the flow of energy in light or infrared energy to change as it moves through the system. So you increase the amount of methane or carbon dioxide in the atmosphere, it absorbs infrared radiation, it's a radiative forcing agent. It's going to change warming patterns in that. You take a coniferous forest that's dark green, chop it down, replace it with a more reflective pasture, that's a radiative forcing agent. You've changed the reflectivity, the albedo. A volcano blows its top and introduces aerosols up into the stratosphere. They will absorb some of the sunlight. For a couple years, the stratosphere will be warmer than it would otherwise be, and the surface will be a little bit cooler. Those are all radiative forcing agents. So they're in the system, but they're kind of external in that they're not part of your F equals MA and all the stuff that comes from that. So they're going to force a change in the flow of energy through the system. We need to keep track of, if we divided the planet up into 4 concepts, or submodels, if you want. We kind of think of it as there's an atmospheric circulation and radiation branch. There's going to be an ocean circulation branch. Actually, in most global climate models, this is the one that has most of the computer time on the ocean, not on the atmosphere. There's going to be a land physics and hydrology component and a sea ice component. That's kind of traditionally how you can view what the different parts are. In the past decade or so, there are now a new branch of models that build upon those. So we now have really two branches. We still have those physics-only models I just kind of described, but now there's things that often get called Earth system models, where now they're including biology and chemistry in it. So if you want to have an interactive, a prognostic, a predictive carbon cycle, you need to include representations of a lot more things. Plant ecology, what's going on in the ocean. I get to go to seminars where I hear about fecal pellets from fish and how they move carbon down to the bottom. Whoa, exactly what I wanted to do when I was in undergrad. But it's all part of this interconnected system. And so the models get more complex. And we add things not for the sake of adding them, but once they're understood well enough, once that theory is there, that understanding, so it can be converted to computer code that we can rely on, because we don't want to just add additional degrees of freedom in a model if they're not well constrained. So that's how we go. So we refer to these as dynamical global climate models. Dynamical to separate them out from statistical. So they're starting with F equals ma, the equations of motion for a fluid on a rotating sphere, conservation of energy, law of gravity, pretty basic. Equations of state, we know how the density of seawater changes with temperature, salinity, and pressure. You have things you can measure in a laboratory as well, right? You can put infrared radiation of a known wavelength through a tube with a known concentration of gases like methane, and you can measure how much is absorbed. So there's a lot of things that are known either, just from the physics like F equals ma, or that are measured and known to a very high degree of certainty, and that's the core of the models. And they can be applied to the different components. The models are also time dependent. Some people, probably you guys got it, but you probably interact with some folks who actually think these models must be like the models they're used to. Like if it's an economist, they assume everything's a spreadsheet. And so you change a number, hit return, it propagates through, and you get your final answer. But these are models that are marching through in time. They're time dependent. The different components are constantly interacting with each other. So how do we construct it? We divide the planet into millions of three-dimensional grid boxes. This is a very coarse resolution version. What's now the workhorse model that I have most recently worked with at GFDL divides the planet up into, I think, 55 million boxes. And on each one of those boxes, there's thousands of equations describing all those different physical things going on, marching through on time steps of order 10 minutes or so. Get the idea on why we end up using those big computers to do all that, with all of them interacting with one another. At the core of those basic physics equations, but we also have to do something called parameterizations. Right? So the answer to your question, if you had it, of why, if you're just based upon physics and F equals ma, why do we have to have different climate models? Wouldn't they all just give you the same answer? Well, a lot of the difference comes down to parameterizations. Even if we make the boxes as small as we can, given the computers we have now, there are things that are important to the climate system that we're not explicitly representing. You're interested in the hydrologic cycle? We are not simulating each drop of water that can evaporate from each white cap on the ocean. We have a grid box that is 100 kilometers on a side. So we have equations, statistical representations based upon observational measurements that say when you have this sort of wind speed and this sort of humidity and this sort of sea surface temperature and other things, this is the kind of rate of evaporation you would have over that spatial system. You heard when Dean Moore was here, the discussion about what about the cloud feedbacks and that. Now you're dealing with individual droplets, not just what the humidity is and how much moisture is in the air, but with cloud condensation nuclei. How many are there? Do you end up with a lot of small droplets or fewer big ones? Makes a difference. So the models can get more sophisticated in that those parameterizations can become more physically based, but as long as we're not explicitly representing each thing, there's going to be something that looks a little bit more like a statistical model embedded inside the physics. And increasingly we throw in biology and chemistry. So It's much more than a spreadsheet. And as lovely as this room is, there's no clock in the back, so I'm going to check my phone every so often. If you have interest in this, I can point you to a website where we actually put together some videos a few years ago to try to explain a couple of the basics about climate models that I've gotten some good feedback from people who have shown them to their classes. Anyway, so those global climate models can do all these wonderful things. I mean, really, it's on a stamp. It's got to be good, right? But they may not be good for the application that you want. That grid box may be too big. I may be happy that the grid boxes now are 75 kilometers or 25 kilometers or 50 kilometers on the side instead of 400 kilometers when I first started working. But you're interested in something on a, I don't know, Carlos, what do you say, 800 meters scale? So the global climate models are useless to you. You need 800 meter resolution. What are you going to do? Also, the models have biases. They're not perfect. They're a global climate model. One of the great questions I get is, why don't you guys just get, now fill in the blank better, the seasonal cycle of precipitation in Cleveland, Ohio better? Or you're 2 degrees too warm in August on the southern tip of the light. It's a global climate model. 3-dimensional atmosphere, 3-dimensional ocean, it's not going to be perfect. So, but for your application, if you're trying to figure out the corn yields in the farm in Iowa, you can't plug in temperatures that are 2 degrees off. You're going to get a different answer. Your precipitation, if it's 20% off from the climatological average in your model's climatology, that's not a good starting point. It's biased. It's flawed. It's not good. So, downscaling often gets done to try to address those two things, to try to give you finer spatial resolution and to address some of the biases or other distribution shortcomings of the model. So there's 2 different kinds. There's something called dynamical downscaling. I won't talk about that too much. You're going to get it as regional climate modeling, where you can take the output of a global climate model and use it to force a model that's at higher resolution but still physics-based, just over the area you're concerned with. You can get finer spatial detail. Some of those parameterizations you had before you won't need anymore. You'll represent orography better, so you'll get rain shadows and things like that better. But you can still have some biases. So regardless of whether you're using a dynamical regional climate model or a global one, you may need to do statistical downscaling. And, well, we'll get into that a little bit. So here's a figure just trying to do the short comic book type version of what statistical downscaling is. It's viewed as a refinement step. It's assumed to be a value-added step. It probably usually is. It's used to transform or translate the raw global climate model, GCM global climate model or general circulation model, output into a form that's more suitable for that climate impacts research. So what you can do, in a nutshell, is take your global climate model, which is that too coarse of a spatial resolution, has biases, and you compare it, you contrast it with observation-based data that's at the spatial resolution that you want, and you view as being the truth because it's based on observations. And by comparing the two, you can have a statistical method that could be either very simple, you can just check and see how the means are different and just adjust for the bias, or you can do things like what Carlos does, where you use artificial intelligence methods and neural networks. And there's a whole bunch of things in between. The general idea is you're trying to glean from your comparison of how to transform this to look more like that, but still maintain the fidelity of both. So you do the processing, you then end up with a high resolution statistically downscale climate projections, and my bet is that a lot of you, a certain set of you, that's when you think about climate projections you may use in your work, that's the data source you use, the statistically downscaled data, not the stuff I look at, which is the raw output of the GCMs. And then that gets used in a range of different applications. Now, so one thing you should know is there's no free lunch, right? Nothing's perfect. Statistical downscale, yeah, okay, you got to, some of us had to pay for the lunch. statistical downscaling should not be equated with unicorns and fairy dust. Okay? It's not going to fix everything. And it's not going to work the same everywhere, and your application is going to make a difference. Here's just one figure to kind of give an idea. Where we came up with a framework, don't worry about the details, just measuring, so the y-axis here is a measure of, let's just say, error, relative skill or error. The higher up it is, the larger the error, the downscaling didn't perform as well if the value was higher. And what we did is we look at it as it performed for the future compared to the historical period. And we have a green curve here and a blue one. Blue one is within 75 kilometers of the coast area, average over there. The green is over the interior. And what do you see? Oh, the black line is just the US 48 states average, so we can ignore that one. You can see that this downscaling method performed a lot better in the interior than it did along the coast. For this particular variable, for this particular method, don't worry about all the details. The point is, it's not a magical elixir. It may have value added, but you gotta be careful. Also, when did it have its biggest problem? In the summer. Well, if you look 100 years in the future, or 50 years in the future, that's where you're going to have your most novel climates. That's where the temperatures are going to be warmer than anything you had in your observational period. And so when we were doing that downscaling training, back when you were on that previous figure and comparing the observations and during the historical period with the GCM, you didn't have an analog. You didn't have an example like that. You're now kind of maybe extrapolating instead of interpolating. So some of the methods handle that better than others. So anyway, it's a little, be aware, not a magical elixir. Another thing. One word we use, climate, for way too many things in NOAA and everywhere. We often hear about the difference between weather and climate. I like to think of it as instead, as I'll put on my DCAT now, as an initial value problem versus a boundary value problem. What do I mean by that? Okay. Whether I'm making a daily weather forecast for the UITS or a seasonal outlook for whether or not there's going to be an El Nino, or whether we're going to have an above or below normal hurricane season, I am going to be able to make that forecast for the people who do. A skillful one, potentially, if they have a good understanding about the way the system works and they have a really good idea about what the starting point of the system is from observations, right? The initial value. And then you're going to track how the system evolves. If it's a weather forecast, individual synoptic systems, cold fronts, storms, and things like that. For the seasonal forecast, you might be tracking that, the El Nino and how that's developing. But you're interested in that one, those features as they go. And there's going to be a limit to the predictability. You don't expect, or if somebody asked you today whether or not they should have an outdoor picnic on the 4th of July, because there's a limit to predictability. Yeah, you nod, you laugh. I can't tell you. When I was at Rutgers, every third or fourth year, whenever whoever was in charge of organizing things for commencement would change at the university, there'd be a phone call that would come into the meteorology department in, I don't know, late February. Well, we're thinking about commencement at the end of May. Could you give us an idea about whether we need tents or not? Okay. So there's a limit. Why is there a limit? You've heard of the flap of the butterfly's wings. Chaos, Ed Lorenz. Good concept, good old paper to read. Oh, by the way, if you think every paper that is good has to be at least 10 pages long, go check out Ed Lorenz's seminal paper on this. It's like 3 or 4 pages. It's amazing. Used to be able to do that. Anyway, so there's a limit to the predictability. But if we're interested in multi-decadal projections and how they could be valuable. Somebody says, why do I think you can tell me what's going to happen 50 years from now and you can't tell me what's going to happen 50 days from now? It's a different scientific problem. Yeah, F equals MA equals the same. We even use now a lot of the same models, equations. It's called seamless systems. But it's configured differently. To make a skillful projection, again, what do we want to have? A good understanding about the way the system works, that we've represented those physics well in the system, and we want to see the response of that system as being credible to those changes in those radiative forcing agents. We're not interested in the starting point. We're not trying to predict whether the year 2073 will have an El Nino or a La Nina. We want to know how the statistics of that will change. Will they become more frequent or less frequent, higher amplitude or less? You get the idea. So there's somewhat different problems. But we can use the similar models for them, but configure them differently and ask different questions. Okay. So, I'm going to skip this one in the interest of time. Like I said, we were just throwing things together. So here it comes down to the, well, finish with one. I asked you guys, and women, sorry, I'm from New Jersey. Guys is like the nicest way you can have the, if it was Spanish, it would be ustedes, but we don't have that, you know, use doesn't work so well. So you guys is about as good as I can do. You all, it geographically doesn't work. So if we want to get our next generation of global climate models and make it better, there's two main ways we can do it. Yes, they're not the only two, but let's, for our purposes here, think of the two. We can have models that are more comprehensive. By that, I mean they can become more, they can have more parts. When we can make, like for hydrology, when I first started working out, the water bucket, land surface, was a 15-centimeter water bucket. You kept track in the model how much rain fell on it, and the water just sat there until it accumulated 15 centimeters, and then whatever you had in excess of 15 centimeters ran off to the ocean. There was also evaporation there, but there was a very simple water bucket. Now, there's multiple layers, you got vegetation, it's dynamical vegetation. The model's predicting its own vegetation. So you can have a succession of time. Some of the models, though, you run them in historical mode. The Amazon rainforest, a little more like the Amazon savanna, right? So you have these different things that you need to deal with. But you can make the model more comprehensive. More code, more computer time, because it's more sophisticated. But what you need to remember, why would they do that? A lot of people think you would only add that when it made your forecasts better. You ended up with a better simulation of the historical period. Your errors, when you compare it to observations, were better. Now you're thinking like a user. The global climate models are primarily developed as research tools, not as forecast tools. They're developed in order to address scientific problems and to gain a better understanding about the way the climate system works. If we just tried to make our models reproduce the past 50 years better, we'd end up over-tuning them. They'd be, anyway, you wouldn't really want to use them too long. So don't think of them as the same as a weather forecast model because they're being developed for somewhat different applications. They're primarily a research tool, not prediction models that's specific to your place of interest. Why do we at GFDL probably spend more time focusing on the deep North Atlantic circulation than whether the model produces 20% too much or too little precip over Iowa? Because for what we're studying in the long term, for what we're looking to do to build the understanding, it actually matters more. We spent a lot of time on the ocean. Why? If you came in, if you were an alien coming from another solar system and checked out the planet every 50 years, and you want to know if it was gaining heat, you wouldn't care too much about the atmosphere or the surface. That ocean, it's big, it's deep, it has a high heat capacity, and it is slow to equilibrate. So, if you were to look over the past half century or so and ask where the planet has gained heat the most, it's the ocean. So that's why we spend a lot of time on the ocean, because it's connected to the atmosphere and everything else. Finally, you can add comprehensiveness to a model, or we can instead do a brute force method and make our grid boxes smaller, higher resolution, closer to the resolution that you want. When I first showed up at GFDL, this was the world's state-of-the-art global climate model. That's what the grid looked like on the ocean side. About 4 degrees of latitude and longitude on the side. And if you wanted to run that model for 100 model simulated years, it would need to be in the supercomputer 24/7 for a full month. That's what it took to do those calculations. pushing it to the limit. But new supercomputers come by. By 2009, the model, well, you can't even see the grid boxes there, but now we're down to, in the ocean, a quarter of a degree resolution. If you zoom in to the Gulf of Mexico, this is what the ocean grid looks like in what's a workhorse model at GFDL now. If we go back to just the thing that appeared in the previous IPCC report, boxes were more like a degree on a side. You can still figure out that's the Gulf of Mexico. Go back to the 1990s, okay. 1980s. We didn't have to worry too much about Florida in the 1980s in our model. Okay, so I'm going to end there with a question to you. For what you care about, or how you would use information derived from global climate models. What would you like to see? Where would you put your resources for the next generation of global climate models? Comprehensiveness, resolution, or something I didn't even mention? Thanks.